Hello everyone, welcome to the 19th lecture of the course Discrete-time Markov chains and Poisson processes. So in the last lecture, we saw the statement of this theorem which says that if Xn is an irreducible Markov chain, then the following statements are equivalent. That means these statements are if and only if. Fine. So what are the statements? The statement 1 is every state is positive recurrent. Statement 2 is some state I is positive recurrent, and statement 3 is the Markov chain has a stationary distribution pi. Moreover, when 3 holds, pi I equal to 1 over mi for all I in S. So this theorem basically says that if you have an irreducible Markov chain, then if it has a stationary distribution, then it is unique and it is given by 1 over mi, where mi is ei of ti, and also if it has a stationary distribution, then all states are positive recurrent. Fine. Now there are various implications of this theorem. So the first is like, so if you are given an irreducible Markov chain and you are told that okay, all states are positive recurrent, then you know then that Markov chain has a unique stationary distribution, and the stationary distribution is given by pi I equal to 1 over mi or 1 over ei ti. That's one way of interpreting this theorem. Now for finite state Markov chains, you know that there always exists at least one stationary distribution. We have already seen this result. So if you are given a finite state irreducible Markov chain, now since it is irreducible and finite state, so you know that there exists at least one stationary distribution, right? But that is because just it is a finite state Markov chain. Now since it is irreducible, by this theorem you know that the stationary distribution is unique, and also it tells you that all states are positive recurrent and the stationary distribution is given by 1 over ei ti. So if you are given a finite state irreducible Markov chain, then all states are positive recurrent. Fine. Remember again, we saw is another result that if you have a finite state Markov chain, then it has at least one recurrent state. Fine. So if it is irreducible, that tells you that all states should be recurrent. If it is a finite state Markov chain, we saw the result that it should have at least one recurrent state. It is not possible that all states are transient. Now if in addition you are also told that the finite state Markov chain is irreducible, since these transience, recurrence are class properties, so that will tell you that if you have an irreducible finite state Markov chain, then all states are recurrent. But now via this theorem we get something more stronger. We get that if you have an irreducible finite state Markov chain, then all states should be positive recurrent. But remember, finite state is important because it's when finite state you know that there exists at least one stationary distribution, and then you can use this theorem. Fine. So if you are given an irreducible finite state Markov chain, then all states are positive recurrent and it has a unique stationary distribution given by 1 over ei ti. Fine. And if it is not finite state, if it is any irreducible Markov chain, then the existence of a stationary distribution is not guaranteed, but if it exists, then it has to be unique and all states has to be positive recurrent. So these are various implications of this theorem. So it is a very, very important theorem. Now we will move on to proof of this theorem. Fine. Okay. Now, so in order to show that all these statements are equivalent, what we will show is 1 implies 2, 2 implies 3, 3 implies 1. So that will complete the cycle, and hence all the statements will be equivalent. Fine. So we first start with 1 implies 2, but that's obvious, right? Because 1 says every state I is positive recurrent and 2 says some state I is positive recurrent. So 2 is a much weaker statement, right? So if every state is positive recurrent, then obviously some state is positive recurrent. So 1 implies 2 is obvious because 2 is a weaker statement as compared to 1. Fine. So 1 implies 2 is obvious. Now 2 implies 3. So what we start with? We start with that some state I is positive recurrent. Fine. Now if I is positive recurrent, then it is definitely recurrent, right? So positive recurrent means it is recurrent plus, so it is have something more, that EI of Ti is also finite. So positive recurrence, if a state has to be positive recurrent, it has to be first recurrent, right? So also you are given that the chain is irreducible, so that tells you that the chain is recurrent, or in other words, every state in this Markov chain is recurrent, right? Now we have seen this theorem right in the beginning of this start of this module on stationary distribution, that if you have an irreducible recurrent Markov chain, this gamma I, which was defined in terms of the expected number of visits, is an invariant measure. So we saw this as a theorem, right? But now what is gamma I? Now recall just the definition of gamma I. So what was gamma I? So what was gamma ij? It was sum over k running from 0 to Ti minus 1 EI delta j of, sorry, not xn but xk. Correct? So this is basically the expected number of visits to state j between until the first passage time to state I. Now if I sum it over all j, now if I sum this over all j, then this in between the chain must be in some state, right? So it is what? So basically what I am doing is I am doing it sum over all j, right? When I am doing it sum over all j, and then if I do k running from 0 to Ti minus 1, this thing EI, then now see in between. So it is when you are doing gamma ij, you are looking at the number of visits to state j between 0 to Ti minus 1. But now when you sum over all j in the state space, that means this sum should be what? Because see, this delta because each xk will be equal to some j in the state space, right? So when you sum over all j, this sum will be basically equal to, so like this del j of xk will be equal to 1 for some j, right? And you are summing over all j, so finally this sum will be nothing but just EI of Ti, which is just equal to Mi. So if you sum gamma ij over all j, that is equal to Mi. That is just from the definition, right? And since you know that I is positive recurrent, you know that EI of Ti is finite, so Mi is finite. Now, so again, remember what is the difference between invariant measure and invariant distribution. So invariant measure, so the difference is for that in case of an invariant distribution, the sum of the entries should be equal to 1. So now for an invariant measure, if I know that the sum of the entries is finite, then if I just divide by that sum, if I divide each entry by the sum, now that will become a distribution, right? Because now the sum will become 1. Because what I am doing, I am taking an invariant distribution for which I know that the sum of the entries is finite. Now if I divide by the sum, that means what is like basically called normalization. So if I divide by the sum, now if I look at this new invariant measure, it is actually an invariant distribution, right? Because I have divided each entry by the sum, right? So if I look at this new pi j, which is gamma ji over mi, where mi is the sum, then this gives an invariant distribution, right? So starting with a positive recurrent state, we have shown the existence of an invariant distribution, which we get in this way. So since it is invariant, since this is irreducible and recurrent, we know that this gamma and I is positive recurrent. So we know that this gamma I is an invariant measure. Now since I is further not just recurrent, so if it is just recurrent and irreducible, then we know that gamma I is a stationary measure, but we know something more here, that I is not just recurrent but positive recurrent. So we now know that the sum of the entries of this invariant measure is finite, so we divide by that sum and make it an invariant distribution. Fine, and thus we have shown that the existence of an invariant distribution. Fine, okay. So we have shown that 2 implies 3. Now we will show 3 implies 1, that if the Markov chain has a stationary distribution pi, then every state is positive recurrent. Fine. So we are now trying to show 3 implies 1. So consider any state k. We need to show that k is positive recurrent. Now we are assuming that the Markov chain has a stationary distribution pi, right? So since this is a stationary distribution, the sum of the entries is equal to 1. Now if the sum of the entries is equal to 1, there exists an I such that pi I is strictly greater than 0. Fine, because if the sum has to be 1, everything cannot be 0. So pi I is strictly greater than, for there exists an I such that pi I is strictly greater than 0. Now also recall, we have, again, although we don't need it here, but recall that we have shown that if it is an irreducible Markov chain, then if one state is and if you have a stationary measure, so that in that case either the stationary measure will have all the entries 0 or all the entries positive. You will see the similar kind of argument we will use here. So now since this sum is 1, there should exist at least one I such that pi I is strictly greater than 0. Now by irreducibility, there exists an n such that p I k n is strictly greater than 0. Remember, so we have started with some k, and why this is true? Because this is irreducible. So you can go from I to k in finite number of steps with positive probability, which means there exists an n such that p I k n is strictly greater than 0. But now if I take pi k again is by we know this property of pi k, that pi k is sum over j in S pi j p j k n. So this is not exactly the property in the definition, but what we get, that pi p to the n equal to pi, sorry, not p, so this is also true if pi is a stationary measure, or so here it's a stationary distribution, and a stationary distribution is obviously a stationary measure. So this thing is true, but now you know now, so this obviously this sum will be strictly greater than 0. Why? That is because one of the terms here is pi I times p, so one of the terms here is pi I p I k n, correct? But now since pi I is greater than 0, p I k n is greater than 0, so we get that this is greater than 0. So if one term is strictly greater than 0, and these are all non-negative things, so the sum is strictly greater than 0. So what we got is pi k is also greater than 0. So this is basically the same argument which we used to show that if the Markov chain is irreducible, then if you are given a stationary distribution which is not 0, that means not all entries are 0, then all entries should be positive. So if you have a irreducible Markov chain and if you are given a stationary measure, either all the entries will be 0 or all the entries will be positive. So but here, since we are looking at a stationary distribution, so it is not possible that all the entries are 0, because if all the entries are 0, it will not sum up to 1. So now that tells you that all the entries should be positive. So this is the same proof which we saw earlier as well. So what we get is pi k is strictly greater than 0. Now we define lambda I to be pi I over pi k. Fine. Now why am I doing this? Now then, lambda is an invariant, because see, pi was a stationary distribution, so in particular it's a stationary measure, and if you multiply a stationary measure with a constant, it remains a stationary measure. This I have already told you before. So if pi is a stationary measure, then if you multiply with some c, real number, some constant, then that is also a stationary measure. Now this lambda I, so since we are multiplying with, so pi I was a stationary measure, it was something more, it was a stationary distribution, but never mind. So pi I over pi k is again an invariant measure or a stationary measure, whatever, one and the same thing. But when I am doing this pi I over pi k, then lambda k is equal to 1, because what is lambda k? Lambda k will be pi k over pi k, which is equal to 1. But now what we have, this is an irreducible Markov chain, and lambda is an invariant measure, or it's a stationary measure with lambda k equal to 1. So now we saw in a previous theorem that in that case lambda should be greater than or equal to gamma k, right, where gamma k is that stationary measure defined in terms of those expected number of visits. So we saw this in a previous theorem, right? If it is irreducible and if you have an invariant measure with this property that the kth component is equal to 1, then lambda is greater than or equal to gamma k. That means lambda I is greater than or equal to gamma k I for all I in the state space. So this follows from previous theorem that we saw. Okay. So what we are getting here, so remember we are trying to show that every state is positive recurrent. Fine. So we need to show that. Okay. So actually, once we show that this, this pi k is strictly greater than 0. Now this lambda is greater than or equal to gamma k. Okay. Now if I now do this mk, what is mk? Mk is gamma I k. Now this we have already seen. Why? So this is basically the same thing that we saw here, that if I sum over all the entries of gamma ij, then it is mi, but in this case we are looking at k. So mk is equal to this. That is just because of the definition of gamma ik. But this gamma ik, but what we saw here, that this lambda is greater than or equal to gamma k, and lambda is defined in this way. So using this, what we get, that this is less than or equal to this. Now since each gamma ik is less than or equal to pi I over pi k, so this sum should be less than or equal to this sum. But now what is this sum? Remember, pi is a stationary distribution. So and this, so this is sum over I, so this k will actually come out of the sum. So this is just basically sum over pi I 1 over pi k, sum over I in S. But since this is a stationary distribution, this sum is actually equal to 1. So you get that this is equal to 1 over pi k, fine, which is strictly less than infinity. Why? Because you have already shown that this pi k is strictly greater than 0. So mk, remember what was mk? Mk by definition is ek over tk. So in order to show that k is positive recurrent, we need to show that ek of tk is finite, and that's precisely what we have shown. That is because this, in the previous slide we already showed that pi k is strictly greater than 0. So mk, which is by definition the sum of these gamma ik, sum over I in S, but now this gamma ik is less than or equal to this lambda I, which we defined in the previous slide. So this sum is less than or equal to this sum, but this sum is nothing but 1 over pi k, using the fact that this pi I is a stationary distribution, so its sum is equal to 1. So we get that, and since pi k is strictly greater than 0, we get that mk is less than infinity. Fine. So thus k is positive recurrent. Fine. So that's what we wanted to show, that if the Markov chain has a stationary distribution, then every state is positive recurrent. So k was a generic state. We started with any state k and we showed that k is positive recurrent. Fine. Now remember, this is, so that completes the equivalence of these statements, but we still need to show this uniqueness of stationary distribution, but that's very simple. Why? Now we have already shown that every state is positive recurrent. So in particular, that means every state is recurrent. So now again go back to that same theorem from where we got this. So if it was just irreducible, we got this greater than or equal to, but in the if you recall the statement of the theorem, it said that if actually it is not just irreducible but also recurrent, then this stationary measure whose kth component is equal to 1 is actually equal to gamma k. So this, now we know that this chain is irreducible as well as recurrent. So this lambda is not greater than or equal to, but actually equal to gamma k, right? Hence now this thing where, so here what we got inequality, here we'll get an equality, and finally we get that mk is equal to 1 over pi k, which is precisely what we wanted to show. Fine. So that completes the proof of this theorem, right? So never mind the proof, but the theorem is very, very important because it gives us so many implications. Fine. Okay. But before going to the example, just let me repeat the situation again. So if you have an irreducible Markov chain, then if it is finite state, then it has a unique stationary distribution, all states are positive recurrent, and the stationary distribution pi I is given by 1 over ei ti. Fine. But if it is not finite state, if it is irreducible but an infinite state Markov chain, then existence of stationary distribution is not guaranteed. So, but if the stationary distribution exists, then it is unique and all states are positive recurrent. Fine. So for a finite state irreducible Markov chain, you already know that there exists a unique stationary distribution. But if it is an infinite state Markov chain, then one way of showing that, so there are these two ways. So if you can actually show that there exists a stationary distribution, then you know that, okay, all states are positive recurrent. But if you also can show so that, okay, all states are positive recurrent, then also you can claim that it has a unique stationary distribution, which is given by 1 over ei ti. Fine. So the situation is much simpler for a finite state Markov chain. So if it is irreducible, then there exists a unique stationary distribution. But if it is an infinite state Markov chain, there may or may not exist a stationary distribution. But if it exists, it is unique and all states are positive recurrent. Similarly, if you can show that for an irreducible infinite state Markov chain, all states are positive recurrent, then also you can just claim that, okay, that the Markov chain has a unique stationary distribution. So for an infinite state Markov chain, if you have to just claim the existence of a stationary distribution, then either you need to show by like straight from the definition of invariant distribution or stationary distribution that, okay, you can find a solution to those set of equations, or if you can show that every state is positive recurrent. Again, you don't need to show every state is positive recurrent because it is irreducible. If you can show one state is positive recurrent, then you know that every state is positive recurrent. Also, again, that follows from the previous theorem. So, you know, if you are given an irreducible infinite state Markov chain, and if you can show that at least one state is positive recurrent, then all states are positive recurrent, and it has a unique stationary distribution given by 1 over EI TI. Fine. Now, till now, we have not given any example of an infinite state irreducible Markov chain where a stationary distribution exists. Remember, the example we have given are all like where stationary distribution does not exist. Fine. So, we have given examples where stationary distribution does not exist. Now, we are going to see an example where of an irreducible infinite state Markov chain where stationary distribution do exist. Fine. Now, let us look at that example. So, what is that? So, again this is the Markov chain with state space 0, 1, 2 and so on, and transition probabilities. So, you can go from 0 to 1, you go from 0 to 1 with probability 1, and then if it for all I greater than or equal to 1, you go from I to I plus 1 with probability half, or you just return to 0. So, how is the chain? So, the states are 0, 1, 2, so 0, 1, 2, 3, 4. So, from 0 to 1 you go with probability 1. Now, from 1 you either go to 2 with probability half, or you go to 0 with probability half. Similarly, from 2 you either go to 3 with probability half, or you actually return to 0 with probability half. Fine. So, that is how the Markov chain is. So, it is an infinite state Markov chain, and again it is easy to see that it is irreducible. You can go from any state to any state. Fine. So, you go from 0 to 1 with probability 1, and for any I greater than or equal to 1 with probability half, either you move to the right. So, you go from I to I plus 1, or with probability half you return back to 0. That is the transition mechanism of the Markov chain. Fine. Now, again as I said, it is easy to see, if you just look at the transition diagram, it is easy to see that this is an irreducible Markov chain, but it is an infinite state Markov chain. Now, let pi be a stationary distribution. Then first of all, okay, now again remember, so I said like how do you write the equations for stationary distribution? So, in the expression for pi I, the sum, so what is basically pi j? Pi j is sum over I pi I Pij, right. So, the sum is over all those states from where you can go to j. Fine, because if you cannot go from I to j, then this Pij will be 0, and hence it will not contribute to the sum. So, the sum is over all those states from where you can go to j. Now, if I look at pi 0, you can go to 0 from any state, right, not from any state, from 1, 2, because from each state you go to 0 with probability half. So, the equation for pi 0 is this. Now, if you look at pi 1, you can go to pi 1 only from 0, fine, and that is with probability 1. Fine. So, you can go from 0 to 1 with probability 1. So, for pi 1 the equation looks like this. Now, pi 2, from pi 2 you can go from 1 only, right. You go from 1 to 2 with probability half. So, pi 2 is equal to pi 1 by 2. There is no other state from where you can go to 2, right. So, pi 2 is pi 1 over 2, but pi 1 is pi 0. So, this becomes pi 0 over 2. Similarly, pi 3 you can only go from pi, or so in state 3 you can only go from state 2. So, pi 3 is equal to pi 2 over 2, but pi 2 is again pi 0 over 2. So, you get pi 0 over 2 square. So, in this way if you proceed, you will actually get that pi n is equal to pi 0 over 2 to the n plus 1, fine, for n greater than or equal to 1. Okay. Now, since it is a stationary distribution, we need that this sum should be equal to 1. So, now if I sum it over, so pi 0, now pi 1 is pi 0, pi 2 is half pi 0, pi 3 is pi 0 over 2 square. Now, this should be equal to 1, but now I take this first pi 0 out. Now, if I look at this part of the sum, then this is nothing but a geometric series. So, which will add up to 2. So, you get pi 0 times 1 plus 2 is equal to 1, or which tells you that pi 0 is equal to 1 over 3. Now, once you have this, you now get the state. Again, since this is an irreducible Markov chain, then obviously it has a unique stationary distribution. Fine, and so the unique stationary distribution is now given by this, because now you know what pi 0 is, and remaining you know in terms of pi 0. Pi 1 is pi 0, pi 2 is pi 0 over 2, pi 3 is pi 0 over 2 square. Similarly, pi n is pi 0 over 2 to the n. So, you get this as the unique stationary distribution. Now, if we use that theorem, we also can tell that each state of this Markov chain is positive recurrent, right? And also you can say, for example, if I ask you what is EI or say E0 of T0, so starting from 0, what is the expected time to return to 0, then that should be equal to 1, that should be equal to 3. Why? Because pi 0 is equal to 1 over, sorry, let me write this little clearly. So, pi 0 is equal to 1 over E0 T0, right? And you know that pi 0 is equal to 1 by 3. That tells you E0 T0 is equal to 3. Similarly, you can find for other I, EI of Ti, right? So, this stationary distribution also give you those informations that, say, if you consider the set 0, what is the expected time to return to 0? It is equal to 3. Fine. So, you get all those information from the stationary distribution using the theorem which we proved today in today's lecture, right? So, this is an example of an irreducible infinite state Markov chain which has an unique stationary distribution, and we have explicitly calculated what that unique stationary distribution is, right? So, till now we have seen now all kinds of examples. We have seen example of a finite state Markov chain which has a unique stationary distribution. We have seen example of a finite state Markov chain which has infinitely many stationary distributions. In that case, it was not an irreducible Markov chain. You can go back to that example and check, because remember the matrix there was, it was the identity matrix 1 0 0 1. So, basically it had two states and both states are absorbing states. So, it had two classes. Fine. So, it is not irreducible. And then we saw examples of irreducible infinite state Markov chains which does not have a stationary distribution. And then finally, we saw here an example of an irreducible infinite state Markov chain which has a unique stationary distribution. So, if it is irreducible for finite, it has a unique stationary distribution. If it is infinite state, either it will have no stationary distribution like we saw for, say, simple symmetric random walk, or it will have a unique stationary distribution like we saw for this particular example. Fine. So, we will stop here today. Thank you all.